Started or not?
No, sir.
Yeah, now.
Yes, sir. Yes, sir. Yes, sir.
Okay, good. Thank you for doing it. So this is series parallel reactions. Uh, B is in parallel and R is in series. It's a irreversible process. You can write for the different RAs is K1 CACB minus RA. Like that RB is also negative because it is reacting. So minus RB, if you want to write how much is disappearing, K1 CACB and K2 CRCB, right? So both will come because it's a positive, this plus this, because disappearance is happening for both. Here negative I am putting because I am putting positive here. Okay. So now RR is the formation. Here it is formation and here it is disappearance. So you want net rate of formation. So formation minus the disappearance. So formation is K1 CACB minus K2 CR and CB. And formation of S is nothing but only one reaction, right? So RB and RR is what is more important now, because B is in with respect to B it is parallel reaction, and with respect to R it is series reaction. Right? So what can be done? Let us do some quantitative analysis, and then we go for let us do some qualitative analysis before going into the quantitative. Again, qualitative, quantitative both will come, right? So let us do some qualitative analysis. Now, if I add like this is the reaction, this is the beaker, and if I add A, one by drop, what will happen here? B is inside, so B is more, right? A is putting drop by drop, so A is less. So what kind of reaction, what kind of curves you will get? Now this is the reaction. A plus B gives R plus B gives S. So B is in excess and A is being added drop by drop. So what could have been happening? Just see here. A plus B is giving R and R plus B is giving S. So now you see A, the concentration drops, right? B concentration is dropping, right? A concentration is also here it is increasing. Moles of A is added differentially. So all A is consumed with A's addition. So the moment you add A, it gets consumed because less of A is there, more of B is there. Therefore, it gets consumed and forms R. So R value goes on increasing. Then what will happen as R forms? Then it reacts with B because B is excess. Then it gives you S. Correct. So you can see B concentration is going down. R concentration is increasing. Again, it makes the steady state because again it decomposes to give you S. So is it the only way? Can we flip this? If you are adding A differentially or drop by drop, this is how the curves will come. Now, what I do is, instead of B here, I take A inside the beaker and put B differentially. Then what could have happened? Now B is differential, A is inside the beaker, or A and B are putting inside the beaker contents immediately. So for both this, the curves will be like this. Now you can see A starts decreasing. A and B also starts decreasing because both are together. A concentration. B is as soon as it enters, it is getting consumed. Now R goes to a maximum and then drops. again S combination will go because R is series, right? R is series. So it goes to a maximum and then falls because S is being formed. What is the difference between these two? Why there is no R maximum here? Why there is no R maximum here? Whereas you get a maximum R here when B is added differentially, or A and B is added together, both will come the same. What could have been the reason why R will be having a maximum? One second. Yeah, R goes to a maximum and then drops. If I do this, there is no R maximum or something like that. What could have been the core reason? Yeah, someone is trying to talk. What could have been the reason? Yeah, what could have been the reason? Any idea?
Concentration difference.
Any other? Now you see, this is the thing which we are going into. Now let us take add A slowly to B, right? So this is what is happening here. A is slowly being added to the B. So you are getting this type of curves. Why it is coming? Just I will read it. Just go through it. For the first alternative, pour a little at a time into the beaker containing B. So continuously you are stirring it, right? As the moment A is added, it is getting consumed. That means R is being formed. Since A is not there, R is there, R is formed. The formed product again, it reacts with B. Some of you can mute it. So here there is no A present because the moment A is coming, because less of A is there, it is getting reacted to give R. Since R is formed and B is more here, so it gives you S. So that is what is happening here. So the R, as soon as it forms, it reacts with B, excess of B, and then gives you S. That is why you are not having literally R present here. That is what he is just trying to give. For the first alternative, pour A little at a time into the beaker containing B, stirring thoroughly and making sure that all of A is used up, because all of A is used up here. And then the reaction stops before the next bit is added. The moment one bit is added or one drop is added, it is getting reacted. So it is waiting for the next drop to come. With each addition, a bit of R is formed inside the reactor or inside the beaker. But this R finds itself in excess of B, so that it will react further to give you S. The result is that at no time during the slow addition of A, R will be present. There is no R present because the moment R is formed, it is in the excess of B, therefore it gets reacted to give you S. The mixture, yeah, that's what here. The result is that at no time during the slow addition of A, R will be present in any appreciable amount. The mixture becomes progressively richer in R, yes, and poorer in B, because B is, yeah. Someone is talking. Someone is talking. Shall I continue? What happened? Shall I continue? Hey man, you are there or not? 50 people are there. Not even one is talking.
Yes, sir.
Maybe some disturbance. So now here, since A is disappeared to give you R, R is again disappeared to give you S. That is why, that is what you are seeing here. B is there, B is concentration is dropping, S concentration is increasing. After some time, S will be a constant because B is over, B is getting depleted. The moment A is being added, still more, what happens? B is depleted, therefore the entire concentration of A is going to increase. Understand? Whereas S concentration is same because B is over. B is over, there is no formation of S. So whatever is there, it will be remain the same. That is what it is being shown here. This continues until the beaker contains only S. Right? So what will happen the next one? Now this, let us use this now. Now same logic can you give this? Now B is added to A. Now what could be the reason now? Other reason I informed you. Now what could have been this reason now? Why R is maximum? Yeah, any idea? There is no B at all here. There is no B at all here. Yeah. Any idea? Can you give the logic now? Think.
The parallel reaction won't happen.
Yes, B is going to be competed with A and R because R and A will be competed with B. That is why there is no concentration of B because B is in parallel here. So what is happening? The moment B is added, it is getting reacted and forms R. Now in this particular thing, both A and R is there. Both A and R is there. The moment B comes inside, A and R both compete for that B. A competes for B to form R. R competes with A to form S. Correct. So that is why you get like this curve. Right. That's what just I'll. The second one here. When B is added slowly, add B slowly to A. Now pour B a little at a time into the beaker containing A. Again stirring thoroughly. The first bit of B will be used up, reacting with A to form R. This R cannot react further, but there is no B inside the reactor. So both A and R is present. So with the next addition of B, both A and R will compete with each other for the B to be added. Since A is a large excess, it will react with most of the B, producing even more R. This process will be repeated with progressive buildup of R and the depletion of A until the concentration is R is high enough so that it will compete favorably with A for the B added. When this happens, the concentration of R reaches a maximum, then decreases. Finally, after the addition of 2 moles of B for each mole of A, we end up with a solution containing only S. This progressive change is being shown in this particular thing. Okay. Now what is happening here? Now both A and B added together. Still the curve will be same. Why? Contents uniformly mixed before the reaction starts. Yeah, why it is? Again, any logic? Yeah, logic. I will again read here. Mix A and B rapidly. Both and A and B rapidly. Now consider the third alternative, where the contents of the two beakers are rapidly mixed together. The reaction being slow enough so that it does not proceed to any appreciable extent before the mixture becomes uniform. During the first few reactions, increments R itself finds itself competing with a large excess of A and B. In the earlier case, R is competing with a minimum of more of A. But here R is competing with both large excess of A and B. B is also large. Hence, it is at a disadvantage. Carrying through this line of reasoning, we find the same type of distribution curve for the mixture in which B is added slowly to the A, right? So this is one reason, because both A and B are large excess. So continuously it forms R till R is a bit quantity is more. Once R quantity is more, then it forms S. That is why you are getting the same kind of curve, right? So other than that, you want to do qualitative analysis for this. It becomes difficult, quantitative. So from this, what we discussed is irreversible series parallel reactions can be analyzed in terms of their constituent series reactions and parallel reactions in that optimum contracting for favorable product distribution is same as for the constituent reactions. So quantitative treatment, again, it becomes difficult. I'll just go through one of this particular thing. So you can see the series and parallel reactions examples, some examples they will ask for 2 marks. So this is one important example, nitration of benzene. Benzene reacts with HNO3, that is nitric acid, in the presence of H2SO4 to give you this C6H5NO2. What is this? Is it toluene? I'm not sure. Okay. Then this reaction, again, it undergoes HNO3 to give you this. This undergoes, so you can see a series of nitration reactions happening. So HNO3, based on the HNO3, it is parallel, and the other one is series, right? Not only that, there is one more reaction, chlorination of methane. Methane reacts with chlorine in presence of the UV light to give you this CH3Cl and HCl. So it goes chlorination to give you carbon tetrachloride CCl4. This one more reaction, one examples. So some 2 marks questions can be asked. So we'll do quantitative analysis. This is the same thing which we discussed just now. We'll do one quantitative analysis before we wind off this unit, right? So quantitative analysis, if you want to do A plus B is because this I'm not showing here because he will give straight away the formulas because CR max and how you are going to get, you don't know here, right? That is why I'm just showing you here how it will be done. So, but again, it is difficult. It is difficult to even follow. If you can take a paper and pen and then start doing it, then you'll understand much better. So RA is K1CA. R this is the rate of formation. I'll just some increase the thing. Yeah. RA is K1CaCb. RR is K1CaCb minus RS, right? So I'm writing only with A. B, since it is parallel, I didn't write it, but you can write that also. So by taking the ratio of two rate equations, we know that in parallel, it is better always to write one over the other two so that the time differential is gone. That is what we studied. So we are writing R by RA, R by RA, and RR by RA because this is R is the parallel series reaction. B is the parallel, right? So RR by RA. So RR is K1CaCb, this divided by RA is this. So if you cross multiply this by this, it becomes 1 and this becomes positive minus 1 plus K2 by K1 CR by CA. So what is RR by RA? RR by RA is nothing but DCR by DCA is minus 1 plus K1 by K2 CR by CA. So the differential is in terms of CR and here CR term is coming. So you take this fellow this side and then write it. So you can write like this, right? You can write like this. DCR by DA is minus K1 by K2 CA into CR is equal to minus 1. This is again a form of differential equation. So the differential is with respect to CA. The thing is CR. The CR is present here. So this is a first order linear differential equation in the form of dy by dx plus py is equal to q. This is in the form of that y is CR, x is CA, p is minus k2 by k1 CA, y is again CR, q is minus 1. Am I right? So this is what if you're writing this in terms of this, so you are getting p is this, q is this, y is this. The solution for this is this equation. You have to integrate p dx. What is p? P is this. Dx is Ca. So you have to differentiate this. The differential for this is dCa by Ca is ln. So ln Ca minus K2 by K1, because this before is there. A log m is log m power a, you can write, right? So this is the differential for this. And if you find out the integration factor, because any differential solution, there will be a complementary function and integration factor. So, or the general solution. Integration factor is nothing but integral p dx, exponential of p dx. Exponential of p dx is nothing but ln. So integral of what do you call e power ln. So this two gets cancelled out. You are getting this as the integration factor. The solution for it is CR into integration factor is integral Q into integration factor into dCA plus I. I is the integration constant, which you have to do it. So substitute all these terms. CR, you know, integration factor, you know, again integration factor. I you have to calculate. That you have to substitute the limit, right? So if you do that, I you are getting I. Now substitute the limit at time t is 0, Ca is Ca naught, Cr naught is not present. Then you can calculate I. Once you calculate I you substitute here to give you the general solution in terms of Cr. Again, it is very difficult. I'm again rushing through because it's not that important for you. Just to make the notes complete, I'm just talking this. If you are interested, you can go for this derivation. It's very difficult. Again, not difficult. It is what you call time consuming, and you have to patiently do, right? Some LCMs and all. So finally, you are getting CR by Ca naught is this much. Now you need to integrate this, differentiate, because we need to find out what is R, CR maximum. That is what they will do. Yeah, dCr by dA, you are integrating it to 0. To calculate CR max by Ca naught is 1 by E. That is what you get for this kind of reaction. CR max by Ca is 1 by E. That is nothing but 0.368. This comes when K2 by K1 is 1, because it's in the factor of K2 by K1. And then if you substitute this CR maximum there, then you get a time maximum. That is what again derivation here. You can see big derivation. It's not that easy, this derivation. You can see here. So this is the CR max. This is the CR max by Ca naught, K1. That is what just now I'm giving you. This is with K2 by K1 not equal to 1. If the K2 by K1 is equal to 1, it becomes 1 by E, right? So with that, we'll stop here. Again, if you want for a mixed flow, this is only for this reactions, or this equations is only for plug flow and batch. You can do for mixed flow also. Mixed flow tau m is Ca naught minus Ca by minus Ra. That is equal to minus Cr by minus Rr. So you can do the derivation. It's not that required. But here Cr max by Ca naught, you are getting this particular thing. Whereas for plug flow reactor, you are getting K1 by K2, power this one. But in mixed flow, you get 1 by K2 by K1. But again, it's a factor of, again, K1 by K2. So that is what graphically we will be showing. Earlier case we are showing. This shows how much is the formation of what do you call the locus of that R maximum, and it's in the form of K2 by K1. So as the K2 by K1 increases, you can see how it is being done, right? So with that, let us stop here, and I'll show you one problem which is very important in the exam point of view. That problem is, I'll just show you. Yeah, please take down this problem. This problem, lot of times he asked in the exam. Yeah, this problem, a lot of times he asked in the exam. Please take down this problem. Under a suitable conditions, A decomposes as follows. A is giving R, giving S, K1, K2. So you can see here where K1 is given 0.1 second inverse or minute inverse. It is a first order reaction. K2 is also first order 0.1. are to be produced from 100, where is this cursor? Yeah, 1000 liters per hour of feed. So CA0 is given, RR and S is 0. So for this kind of reaction is asking you what size of plug flow reactor will maximize the concentration of R. What concentration? Yeah, what is the concentration of CR in the effluent stream? So he's asking you, if I use a plug flow reactant, what should be the size of the plug flow reactor for the maximum concentration of R? And he's asking you, what is that maximum concentration of R in this? Again, mixed flow also is asking you the same thing. And what is the concentration of mixed flow? If I use a mixed flow, MFR, what will be the CR max? You know the expressions, we can directly substitute the expressions here. So we can see this is a series reactions. So he's asking you to for a plug flow and a mixed flow. We know that this equations you have to use. I'll just go through that equations. Yeah. So we need to go for this equations. This is for the CR max by CA0 for mixed flow, and this is the CR0 by CA0 max by CA0 for plug flow, right? So we can do that, but we'll see how he is doing. So he'll try to derive it and then use it. Again, this is what I'm giving you. If this problem is asked for 10 marks, if you are straight away writing this earlier, yesterday I'm talking about this, right? If you are straight away writing this particular equation, these two, just 2 steps, that's all. CR max by CA0 is this. You already gave K1, K2, then substitute in this, calculate CR max by CA0 in MFR. This is for plug flow reactor. You get very less marks. That is what I'm telling you. So what you have to do is you have to go for a derivation, because this they will ask for 12 marks, or earlier the Anna University pattern is 12 marks. Now I think they will ask for 10 marks. For that, you need to derive for a plug flow reactor derivation. This is the derivation. So this is the same derivation which we already discussed. In this, we know that your plug flow reactor is putting tau p and all is trying to calculate, and you are getting CR max is 0.368 liters. And if you use a mixed flow reactor, you are getting thing as CR max is 0.25 mole per liter. So here, here it is 0.38 moles, and here it is 0.25 moles. So always PFR is better compared to that of MFR, right? So how it is, just go through it. Again, you have to do the derivation. Yesterday I was talking in the class the same thing. If he is giving you a problem, if you are substituting directly the formulas, then it is you cannot expect 10 out of 10. If he is giving you for a 6 marks or something like that, you can directly substitute. Otherwise, you have to do the derivation. This is the derivation. This is in the form of integral dy by dx plus py is q. So that the solution for this is y into integral p dx is integral q into integral e power p dx plus dx plus I. So substitute accordingly. What is r? What is y? Y is cr. X is dt, and p is k, and q is this particular thing, right? So if you substitute all, then you are getting CR e power kt is k CA0 t plus I. I is an integration constant. You have to substitute the limits at time t is equal to 0. There is no R is being formed because it is a series reaction. Only A is present. Then I, if I substitute this, I will be 0. So CR is k CA0 t by k e power kt. So this maximum you will get when you differentiate this. So differentiate and then equate to 0. That is what he is doing. Differentiating because e power is there. That will make the things complicated. So you get t is 1 by k. This is the time which is maximum. You get 1 by k. So T max is 1 by K. You substitute that in that particular equation, you are getting CR max is KCA naught 1 by K e power K 1 by K. So this is if you are something gets cancelled out, KK gets cancelled out. So you are this K gets cancelled out, though you are getting CA naught by E. E is the exponential, right? So for a plug flow reactor, you know that T is tau, tau P optimum is 1 by K. That is what here is putting. So CR maximum is CA naught by E. So tau P is 1 by K. K is nothing but he gave in the problem is 0.1, I think. Yeah, 0.1 in minute inverse. So 1, you substitute there, 0.1, 10 minutes you are getting. Like that, tau P is V by V naught. Volumetric flow rate is given. Then you can calculate the tau P. That is the time required in the plug flow reactor. Volume also is asking you V. V is tau P into V. Therefore, this is 166.7 liters per 7 liters of if you are using in plug flow reactor. You get a CR maximum of 0.368 mole per liter. So if I use in the plug flow mixed reactor, again, your derivation is giving you CA by CA naught is this, CR by CA naught is this. Then you have to differentiate this because DCR you have to differentiate to equal to 0. Then we get CR maximum on tau m. So tau m is 1 by K, as same as that of your plug flow reactor. So tau m for plug flow reactor and tau P for a tau m for a mixed reactor and tau P for a plug flow reactor almost is same. From that we can calculate the V. V is 16.67. Therefore, volume is 166.7 liters. Here also the volume is 166.7 liters. The volume remains same because tau is remaining same in this both the reactors. Either it is PFR and MFR. So we know that for the same volume, the conversion of plug flow reactor much more. The conversion is more in the sense CR maximum will be more. That is what we see here. Again, tau m is 1 by K1 K2, 1 by K square because K1 is equal to K2. So this is tau 10 minutes. CR maximum is CA naught is this particular thing 1 by K2 by K1 half power this. If I substitute here, I am getting 0.25. CR max I want, CA naught I gave, CA naught is 1. So 0.25 moles per liter. Whereas here you are getting 0.368 mole per liter, but here you are getting 0.25 mole per liter. For the same volume, 166 is the volume for a plug flow reactor, 166.7 is the volume for a mixed reactor, right? This problem is very important. Lot of times they gave this problem. It is better you do the derivation just like this, then you get 10 marks. If you are not doing it directly, if you put in this particular equations, then you may not get that 10 marks. This is what yesterday I was talking with you. If the problem is asked for 6 marks, right away substitute and then calculate. But if the problem is asking for more marks, that means that he is asking you to derive it, right? So with that, I think you can see the rest of the problems with in the Gavani or any other book, whatever is comfortable to you. And three more problems I'll just show you. This is the problem which they are giving in Gavani. Some problems will do because still the time is there. Okay, let me reduce. Now you see here, this is one problem. What reaction schemes and conditions would you use to have maximum concentration of R for the following reaction? Now you see A plus B is giving R, A plus B is giving S. RR is 15 e power minus 273 by T, Ca power 0.5 Cb, and RS is 200 e power minus 2000 by T CaCb. So he is asking for a maximum concentration of R. What schemes it is done? So RR by RS, if you do it, then strike out whatever it is there. 15 by 120 is this. E power minus 273 minus 2000. So that is what here. Ca 0.5, Ca, so Ca down it will come, Cb can cancel out. So you are getting Ca power 0.5 at the denominator. So from this, what we can do here, activation energy, because this particular thing is the activation energy 15. This particular thing 273 minus this, and this is the pre-exponential factor. Activation energy for the reaction forming S is more because this is 2000. That it is forming R and S. To maximize this, the reaction should be carried at a low temperature. Then only you get this ratio more. The amount of R formed can be maximized by carrying out the reaction at a low concentration because Ca is down. Ca is down in the sense to maximize this, you have to keep the concentration low. Then this, if this is low, this entire thing will be high. So RR will be high. How you can keep this concentration low? By putting in CSTR. That is what. By putting in a CSTR or using a low pressure things or using a CSTR or even recycle reactor you can use. This is one more way problem which they can ask you for 6 months. So they will give you temperatures also here. Till now we didn't talk about this temperatures, that it will talk in next unit. So this kind of things also they will ask you for 6 months. There is one more reaction here. A is giving R, A is giving S, A is giving T, is giving you the pre-exponential factor, is giving you the E terms and the temperatures. Ca power 1.5, 0.5. So he's asking under how and under what conditions, that is reactor type, temperature and pressure, should the above reactions be carried out to maximize the formation of R. He wants only the maximum formation of R. If you see here, maximum formation of R, you are having the activation energy higher. S is having 2500 and T is having 5000 activation energy. So activation energy for T is very less, whereas R is very high. As the activation energy is very high, you know that activation energy high is the reactions are very sensitive to temperature. Even a slight change in temperature, your reaction shoots up. That you remember, right? So more about this temperature changes, all that we will see in the next unit, right? So go through this. That's the same thing what I just discussed. This is the activation energy. This is the activation energy. So he will discuss about the same thing, right? So like this kind of reactions also, please some bits 6 marks they will ask you. The other problem which I asked you, CR maximum for a plug flow reactor and a CSTR. That's the general problem. Lot of times they ask you in this unit, right? So with that, I think I'll wind off this unit. You can see my presentation is also getting over here. So these are some more reactions. These are much complicated. This is not a series parallel. This is a series parallel, but here if you see, A is giving R, R is giving S, A is giving T, and R is also giving T. This kind of reactions, even irreversible also, if this is a irreversible, there can be a reversible also. These are difficult kind of reactions where we call it as Denby reactions, right? So they'll use like this K34. What is K34? K34 is nothing but K3 plus K4. Like K12 is K1 plus K2. So based on this, they will do, or you can see one more, A giving R, R giving S and T. So these are much complicated here. This is a cyclic process. A giving R, R giving S, and A is giving S, right? So these are wide applications are there, but again, very difficult for you to follow. So even this is irreversible, it can be reversible also. That he is showing you the derivation part in the 11th spill, which if you can follow, you follow, otherwise leave it, right? Just to complete the notes, I'm just giving. K34 is nothing but K3 plus K4. That's because it becomes big terms. That is why they write like this, right? So this is for a mixed reactors. Again, K12, K34, all that, right? So these are some of the problems which they'll ask you in the exam. So your third assignment or third tutorial, this of I think 4, 5, 6, these 6 problems try to solve and then submit to me by this month end, right? I will put today these 6 problems, right? These 6 problems submit to me by this month end, right? I think tomorrow I'll upload that. So with that, this is the problem which I showed you. This is a very important problem, right? So with that, I stop this third unit. Then any difficulties are there, let me know. Anything you want to talk from your side? So Guru, it is 52 people are there. I think -1, it is 51. So 14 people are absent. Please send me the attendance. Yeah, I stop the recording now. So in the next class, we'll